Let's continue our discussion about solving trigonometric integrals using trig identities. This time we'll look at using the half-angle formulas. So we have two half-angle formulas. One of them involves cosine squared of x, or let me call it theta, I guess. And that formula looks like this. It's going to be 1/2 times 1 plus cosine 2x. Okay. For the other formula involves sine squared theta. Whoops, I meant to make that x into a theta. Hold on. Okay. And sine squared theta has the same shape as the cosine squared one. In other words, it's still 1/2 times quantity 1, and then there's a cosine 2 theta involved. But this time, instead of having a plus, you're going to have a minus there. So I hope you guys could see that for both cosine squared and sine squared, the identity has the same shape. In fact, they both involve cosine 2 theta. The only difference is the sign between the 1 and the cosine 2 theta. So in this case, it's the sign that has the negative and the cosine that has the positive. So these are so important. I am going to highlight them, and I really suggest that you memorize these identities. Okay. And we're going to look at an example. Let's take a look at an example 6 here. For example 6, we basically need to apply the half-angle formula. The integral of cosine squared x dx, you apply the half-angle formula, and you're going to get the integral of 1/2 1 plus cosine 2x dx. And then I like to pull out the constant from the integrand. Because it's a constant times an entire thing, I can pull the constant out of the integrand. So then I get 1/2 integral of 1 plus cosine 2x dx. We could split this up. So this could become 1/2 times the integral of 1 dx plus, don't forget to distribute the 1/2 across. So we're going to have 1/2 integral of cosine 2x dx. You might ask, why did you split it? The reason why I split it is kind of lame. I want to use U substitution on this cosine part over here, and I just want to make it super obvious. So let's do that. I can only integrate cosine of something, so I'm going to let the inside part u be equal to 2x, and this tells me that du dx is equal to 2, which means if I wanted to solve for dx, I could write dx is equal to 1/2 du. All right, so let me, for the first part over here, find the antiderivative. The antiderivative of 1 is just x. And for the second part, let's do our substitution. We're going to have the 1/2 integral of cosine of u, and then we're going to have a 1/2 du. So yet again, I see I have a constant times the integrand, so I can move that constant outside, and I'm going to get 1/2 x plus 1/4 integral of cosine of u du. Now I can find the antiderivative quite easily. We have 1/2 x plus 1/4. The antiderivative of cosine u is sine u plus c. Of course, our original integral was in terms of x, so we can't leave it with the u's there. We have to substitute back. So we get 1/2 x plus 1/4 sine of 2x plus c. Okay, so let me just highlight that real quick. This is our final answer. And let's talk about our strategy. So when you have an integral involving both sine and cosine, and those could be raised to certain powers, and when both of those exponents are even, that's when you want to use the half angle formula. All right, so when they're both even, both being the operative word here, then we'd simply use the appropriate half angle formulas. And use substitution. Now, to be honest, going back to our previous example here, a lot of students, they encounter an integral that looks like this cosine 2x so much, and it always kind of has that same shape that they almost do the u substitution in their head. So, you always pick up this 1/2 here, and then you got to move that out in front. Anyways, this concludes our video on integrating using trig identities, in particular the half angle formula. Take care, everyone.